elements and stuff, okay? So that's one thing that they were trying to accomplish. This is back if you go 1700s after we're coming out of like alchemy and all that. A bunch of other guys are going around trying to figure out how matter behaves, okay? They're trying to act like, not necessarily what the things are, but how they behave. And that's what these scientists here that we're talking about are doing. Now, the laws we're going to talk about today, Boyle's Charles, and then we're going to talk about Avogadro and Gay-Lussac later. It's more introductory for where we're headed. And where we're headed is to a unified gas law, a gas law that takes into account all these things. So we're going to learn the basics, the underpinnings of it, how they want to about it, and then combine it all. And in fact, we'll do a lab on one of these. I haven't planned it yet for next week, but it probably should. It can fit the week after. Yeah. Anyhow. So anyhow, we're going to title this section "The Gas Laws." The gas laws. And you're gonna have a good intuitive understanding of this stuff. I mean, it's not like I'm gonna have to like to really convince you about much. The first guy, his name is Boyle. So again, we're always giving credit to these scientists, but to me, it's more the discovery that matters. He said that there was a relationship between pressure and volume. Okay, so let's think about that. If you take a gas and you put it under greater pressure, what's going to happen to its volume?
Condenses so the volume goes down.
It goes down, okay? And if I take a gas and I reduce the pressure on it, the volume is going to go up. What kind of relationship is that, mathematically speaking?
Direct?
No, it's not direct. It's the opposite.
Inverse direct.
It's inverse. It's inverse. As one goes up, the other goes down, right? So like for our wrestlers, an inverse relationship is the more they work out, the more their weight goes down. Does that make sense? So that's an inverse relationship, as opposed to a direct relationship like the more they eat, the more they gain, right? Okay. Hey, let's see. How you looking? Yeah. You be ready? Well, tomorrow you got short periods, but is there any way you can be ready for tomorrow to take that?
Yeah, I can take it after school.
I can't. I've got practice and stuff.
Okay.
And I'm not expecting you to take it today. I mean, you got to get back into the swing of things.
Yeah, that's fine.
Yeah, I would prefer that. If that's a problem, let me know.
All right.
And you guys that were here, you know Patrick's a bright guy. You think you can finish it in a short 35-minute period?
Yeah.
I do too. Most of you guys were done early, weren't you?
I finished mine.
Yeah, you
Don't
finished
mess
it.
up.
If you don't mess up, yeah. Yeah, if you mess up, it can turn into a nightmare. Yeah. Okay. So again, so Boyle's law. So this guy Boyle, he studied that relationship, and he just did the same thing that we were talking about. He tried different pressures and pressures and volumes, and I'll show you that. Haha, yes.
His name is Percy.
Percy.
Freshman.
Percy, nice to meet you, Percy. How you doing? I'm Mr. Markley. Come on in, have a seat. Yeah, why don't you have him sit there? Ethan's not. Yeah, Ethan's not here. So everybody, Percy. Everybody, that's everybody.
Hello, Percy.
They're nice guys, man. They won't bite. If you have any questions, be sure to ask. Okay, so Boyle's law. So I'm going to show you this tomorrow again. I wanted to do it today, but I'm a little worried about time. I have a little chamber over there that I can apply a vacuum to. So that means I can change the pressure inside that chamber, and if I put a balloon in there, I can see what happens to the volume. Okay, so we'll do that tomorrow. But I prefer to do it today, but time is the issue. And so basically he came to the conclusion that there is an inverse relationship. There is an inverse relationship. So as one goes up, one goes down. There's an inverse relationship between pressure and volume. Between pressure and volume. Of a confined gas. So a gas that's held in some kind of container. So basically we can say as the pressure on the gas sample increases, as the pressure on the gas sample increases, volume decreases. Well, that shouldn't be a terrible surprise. No, it's pretty straightforward. And we could say, and vice versa. Have you ever heard that, Gary? Vice versa?
Uh-huh.
You know that one? Okay. So you guys know vice versa?
Yeah.
The other way around, right? So as the pressure decreases, the volume increases, right? The opposite. And that in and of itself is not a horribly huge insight, okay? I think most of you guys could figure that out on your own, couldn't you? Okay. But there's something that he did figure out that's pretty significant. And we're going to do this in lab. We're actually going to do this thing where we're going to change the pressure on a sample, change its volume, and see how they relate. And the way they relate is like this. Pressure times volume equals K. So this is pressure. This is volume. And K turns out to be a constant. And that's what's important. Now, regardless of the units that I use for pressure and volume, regardless of the units, if I take whatever units for pressure I use, I could be using ATM, I could be using kilopascals, I could be using square root, whatever it is, but as long as I use one of those units and I multiply it times volume, doesn't matter if I'm talking milliliters or liters or gallons or whatever it is, as long as I keep it the same. If I take a sample and I apply pressure to it, I measure its volume, and multiply those two numbers together, I get a number. If I change the pressure on this, which the volume changes, and I take those two numbers and I multiply them together, I get the same number for that particular sample of gas. You get that now? Okay. So it's I take those two numbers because they're both changing, but the thing is they change in such a way that they both continue to multiply to the same number. So the neat thing, and this is the insight that's pretty cool that Boyle has, is so you can do this. We can say, so for a confined gas, we can say P1V1. It's P1V1. So that's like saying initial conditions. Well, P times V equals K. Some constant. Well, if I change the pressure and the volume on that particular system, then I'm going to get a final set of conditions. Final conditions. But they're also equal to K. So that basically means I can kind of throw K out. I don't really care what K is. All I know is that the initial conditions, P and V, when you multiply them together, are going to equal some number K. And if you change the conditions, the new conditions, P2 and V2 times each other, are also going to equal K. So we can say P1 and P1 times V1 is equal to P2 times V2. So basically what it's saying is this. If I know the pressure and the volume on a gas, and I know what the new pressure is going to be, I can tell you what the new volume is going to be. I can predict it before it happens. Or if I say, okay, I want to change the volume to this, I can predict what the pressure is going to be. Okay, so right now Boyle's just talking about that. Now, a thing to keep in mind here, and I kind of mentioned it, is for these calculations here, pressure and volume units must agree. Pressure and volume units must agree. So the particular units that you're using, that's not the crux of it. The crux is as long as they match. And you're going to find out later that for some of these calculations, the units are going to matter. So you've got to pay attention to what we're getting there. Okay, Jacob's in the house. Adam Uppelman is in the house. You guys see Peter today?
Yeah, he's good.
He is? Okay. Peter should be on his way. Garrett's on his way too, probably?
Garrett's not here.
He's not here, okay. Thank you. Probably. Oh, I wanted to ask you. Are you from China? Whereabouts? What part of China? Where's that here?
It's his hometown. I'm not sure where it's located.
Okay, but by what big city? By Shanghai.
So it's southeast of China.
yes, so this is cold, and it's not cold today.
Yeah.
Yesterday was a record high.
So around our hometown, the temperature would be around 70, 80
Yes.
in winter. Yeah.
Yes,
it's really
exactly.
warm.
Yes, a little bit warmer.
Yeah, it's totally different.
Yes, yes.
Much warmer.
Yeah, you came on a warm day. Yesterday, did you guys know that?
Yeah,
yesterday we
was
hit
really warm.
58 degrees, and that was a record.
Yeah.
What's 58? 58 is probably like 15, 16, 17 Celsius. Not
It's
that
more
high.
like a 10.
10?
Yeah.
A lot lower.
Exactly.
So, at least you came out good. Because a few weeks ago, what was it?
Like
Friday?
16?
Yeah.
That one Friday we left.
Harvest day was 10, 11,
Yeah.
I think.
What, that's like
Remember that one
negative-
Friday just a couple weeks ago?
Negative.
Yeah, the snow was this deep in the parking lot
Yeah.
when we got out of school. That was crazy. Okay, so the units must be great. All right, so let's do an example here. All right, so let's say if a balloon, and we like to use balloons here because balloons can easily expand and contract, okay? But this applies to any kind of other system. So if a balloon has a volume of 375 milliliters, ml, it's messy, 375 ml, at a pressure of 1 atm. So picture somebody holding a balloon, 375 milliliters. 375 milliliters is a volume of like a Coke can, 12-ounce can. So imagine a balloon like about that big, and somebody's sitting there holding it at sea level, okay? Because they're at 1 atmosphere. What would the volume be? What would the volume be if the pressure dropped to 700 torr? So you can picture this as being like a helium balloon. And so little kids on the beach, and little kids there holding this little 375 milliliter balloon. He lets it go, and then he starts crying and all that, and everybody else watching it fly away. Okay. And so as it goes up in the atmosphere, pressure's dropping because there's less air above you. What's going to be the volume of this balloon at that particular under those set of conditions? Well, let's get this out. Let's see. So first of all, we had a volume. An initial volume was 375 milliliters, and I had an initial pressure equal to 1 atm. I want to know what the final volume will be, V2. I don't know that, but I do know that the units should come out in milliliters because they have to agree. If I was given liters, then they don't come out in liters. And the second pressure they said is 700 torr. Now, we got a choice here. There's no specific reason why we should work in torr or ATM, but I'm going to tell you this. Eventually, ATM is going to be much more important to get to than torr. Okay, because later on in some of our equations, they require ATM. So I just say whenever you have the choice, if going to one unit or another, ATM is probably a better choice. Okay. Now, if on the test you convert it into torr, I'm not going to mark you wrong. Okay. It makes it a little harder for me to correct, but that's totally fine. It's a legit way to go. So if you remember here, to convert this, I would do this 1 ATM. Does anybody remember how many torr are in an atmosphere?
760.
760. So you'll want to memorize these. Torr. And so I come out to be like 0.921 ATM.
But since there's only one ATM, wouldn't it be much easier to just go from ATM to torr? Since there's only one, just say it's 760.
It would be easier, okay? But what I'm saying is developing the habit of thinking about ATM is probably better.